Thanks. Thank you. Good morning. Good morning. Good morning. Very good morning. So, this is actually one of the last topics that I have. I mean, that I was planning on, but we can talk more about, NDE, and tomorrow morning we can, we'll talk about NDE, and then today afternoon Mukhopadhyay is going to talk today, last lecture, and then tomorrow morning I can talk about NDE, and then something about thermal protection structures we can bring in the NDE. Yeah. Yeah. When is your conference exact? Structural integrated next month, right? Yeah, next month. Yeah. Okay, we can start. I'm going to go a little slow on this topic. It's a little bit involved, and I don't have all the answers. Okay, nobody has the answers for this. Actually, they're still struggling to find the real answer, what it is. So. Okay. Should I hit here something? F4 or something? Oh, it's in here, right? The pointer. You took it out? Oh, okay, thanks. Yeah. So. Okay, we'll talk about dwell fatigue. Yeah, dwell fatigue. So before I talk about dwell fatigue, I should probably, this is, let me come out of this for a second. Let me put view, slide sorter. Okay. Okay, so. Good? Okay, so is the battery okay? Oh, this is on. Yeah. Okay, so here we have a waveform that looks like this. Okay, you're going up, ramping up, like an aircraft is taking off, something like that. And there is a little bit of cruise here and then coming down, okay? I think I put here 60 seconds, 1 minute, and then it's coming down. So this is the kind of waveform that people use to understand dwell fatigue in fatigue crack growth, fracture mechanics specimens, or low cycle fatigue specimens also. Those are the two type of specimen configurations we use to understand dwell fatigue. At least that's what we have done so far, okay? And there are I made some remarks here that dwell fatigue, what is dwell fatigue? So it refers to the reduction in fatigue life. So you know that there is a fatigue life by regular cycles, but when you put that whole time, you find that the fatigue life goes down, of a component goes down, okay? As a result of exposing the component to a constant high mean stress, okay? During cruising, between the ramping up and taking off and landing. So that load cycle that you have, the dwell time that you have there, okay, is what can bring down the fatigue life reduction, okay? And you can change that, you can change that mean stress back and forth, up and down. So this cold dwell fatigue, it's cold in the sense that in titanium alloys, it can take place around 120 degrees Celsius. 120 degrees, it's pretty cold temperature for a turbine engine. It's relatively cold, right? And it's a 40-year-old problem. And it was first observed in some titanium alloy discs, okay? Not the turbine discs, but fan discs. In the Rolls-Royce RB211 engines, I don't know exactly what they are, the Lockheed TriStar aircraft, okay? So, here I wrote again, the cold dwell fatigue refers to the phenomena that happens at temperatures approximately 100 degrees C, but it's more 120 degrees C or less in a relatively cold part of the engine. And we're talking about titanium alloys here. You know, we're not talking about aluminum or something. We're talking about titanium, and that's pretty low temperature for titanium, right? 120 degrees is quite low for titanium. So this is a serious problem for the producers and operators because the inspection intervals that we have, we need to check the fan blade and the compressor blade, and all those inspections we have to do periodically. But when you have a problem like this, you're worried about how your disk is doing. So periodic inspections, are required, and the replacement of rotor components, which is same as disk components, in which cracks are detected. So this can happen. This used to happen, and it still happens every now and then, and it leads to the over-design of disks and blades. So it makes the engine more heavy because you don't want to take a chance. Right? And then, sorry, I didn't arrange these this morning properly because I didn't know exactly the flow of this would be. For this class, I thought I should just kind of go slowly, gently a little bit. Let me pull this up. Okay, here we are. So we all know that cyclic fatigue, gives rise to fatigue fracture much below the yield stress of the material, which we already know that. And this remains an unsolved engineering problem till today. So this is a very recent slides I made. This is still we were trying to do this when I left, and they're still trying to do, the group back in Air Force, in Wright-Patterson Air Force Base, they're still trying to do that. Adam Pilchak is the guy. And the metallurgical factors affecting cold angle, well, they are known in the sense that we have a lot of data, but we don't know, actually. I should put here, I should change this line to the metallurgical factors affecting cold dwell fatigue. The data on this there's a lot of data exists, but how to put the whole story together is not very clear yet. I think that should be the way the wording should be. So the mechanisms for this phenomena are less clear. And then let me pull up the third one. Please bear with me. I'm sorry about this, going back and forth. Experimental observations. Yeah, that's perfect. So the experimental observations are titanium 6-4. I'm actually surprised that titanium 6-4, but near alpha alloys are the most affected. Like anything like titanium 6 aluminum, titanium 6242, 811, these are near alpha, means there are more alpha content than beta, more aluminum stabilizers. They're very dwell fatigue sensitive, okay? But you will also see that these type of alloys also have a high degree of crystallographic texture. We'll talk about that in a little bit. And in specimens that exhibit a preference for crystallographic slip, okay? So, okay. Let me just go back now that we have some more audience here. Let me just go back, okay? So we just started to talk about dwell fatigue, huh? We just started to talk about, I know it's hot out there. It's very hot. Yeah, dwell fatigue, humid. So this was we were talking about like a aircraft ramping up, cruising, and ramping down. And you can have many more cycles like that. And then we were saying that what is dwell fatigue in terms of life? It means a reduction in fatigue life, reduced fatigue life. And because of exposing the component or the sample in the laboratory to a high level of mean stress, okay? And then simulating something like a cruise, ramping up, cruise, and coming down, ramping off. And it's a old problem. It's a 40-year-old problem where we find that it happens that at low temperatures, like 120 degrees C, and for aluminum, for titanium, 120 degrees C is not very much, as we just said. And then it happens in the cold part of the engine, so that's like fan. And it's a serious problem because the NDE inspections have to be done more often, and the designers have to do more, over-design so that nothing breaks. So we design more on the safe side, so the engine can become thick. The engine can become heavier because we're using whenever we say heavier design, over-design, we mean thicker. So the part is this thick. If you're having a problem, just increase the thickness of the part, gauge thickness. So the same loads would be applied on a bigger thickness, so the stress will be down. Yeah? So that's over-design. That's how you overcome under-design, by over-designing it. And then, the first statement is very obvious. That should be the first statement at the beginning of the class, actually. Cyclic loading, we know that the stress is much less than the yield stress of the material, so there's no plastic deformation. And cold dwell fatigue, it is an engineering problem, and also I think it's a scientific problem also. Although the operators get affected, the pilots get affected, but in reality it's still a scientific problem. There are a lot of papers are there. People are still working. They work very sporadically. Every 5 years, 8 years, if people get excited, they publish a few papers and then they say, oh, this cools off, and then again, it's like corrosion. Everybody wants to work. Oh, there's a problem. Everybody works. And okay. And then they start again. Exactly same thing here also. So here are some observations. And we said that before you just came, we were saying that near alpha alloys like 6242 with silicon or without silicon. If you put silicon there, 0.2% silicon, it's more a weldable alloy. We add silicon sometimes to this 6 aluminum, 2 vanadium, 4 zirconium, 2 tin or something, right? And then the titanium 811 alpha beta, near alpha alloy with beta phase also there. And these are very crystallographically textured, means they show a lot of planar slip. That means they show a lot of planar slip. The dislocations move in a planar slip. They're very textured. And also texture comes from a different place, which we will see. You already know that, but I'm going to point it out. And there are also a lot of micro textures. So what they are finding is that there are regions in these alloys where there are micro regions in these alloys which are very highly textured. They're happening, in locations inside the material. This is one guy from General Electric, Cincinnati, Andy Woodfield, who said that the microstructural features controlling the dwell response in alpha-beta process titanium's 6242 include size, shape, and volume fraction of MTR, micro-textured regions. Okay? Micro-textured regions, the same thing, MTR. Okay? Size and density of primary alpha grains. So he's one of the guys, I think back in the 80s maybe. His paper is available in the literature, Woodfield, and it's a good paper actually. And then Kasner et al. Also showed volume fractions of primary alpha 6242, increasing volume fractions of primary alpha 6242 resulted in large dwell debit. So what that means essentially is that if I plotted the loss in life, I should make up a graph there. Maybe we'll put it on, would it be okay if I put it on this paper? And then we can transform it afterwards to oh, thank you, Amit. Yeah. No? Okay. Ooh, it's not. I didn't take it out of my bag, so okay. This will work, right? Yeah. So percent loss in fatigue life. So this is dwell fatigue. Percent loss in fatigue life versus percent alpha volume fraction. I don't know how the curve would be, but just let's put it like a dotted line. I don't know exactly it will be like this or like that. So just so that we don't take a risk, we'll just put something, we'll just stop it here somewhere. Maybe 20, 30, okay? Volume fraction. So something like that. So the more alpha you have, more you will lose in the dwell fatigue, right? So this is also dwell fatigue debit, which is same as % loss in fatigue, right? Or okay, so makes sense, right? So we'll go back here, and then we'll go back to the slides. Okay, thank you. Size, shape, volume fraction. Okay. And same thing, we can also plot on that one, maybe on the y-axis, on the other y-axis, microtexture regions. We probably can look at the literature and see how it compares to the loss in life. And then this guy, Sinha, he works at the Air Force Research Labs also. And Adam, Vikas Sinha and Adam Pilchak, they also showed that the size and shape of the faceted regions of the dwell fracture surfaces coincided with size and shape of measured microtextured regions for titanium 6242 and 811. So I will show that in a second. What that means is essentially that the so we'll see on the, because, okay, so this is the thing, right? So there is a generality, again, another generalization, okay? We can put a generalization here. And the generalization is near alpha or more alpha, near alpha, more alpha means more planar slip in terms of deformation. In terms of fracture, that would mean, okay, oops, okay. In terms of fracture, so this is deformation. And in terms of fracture, that means it is more crystallographic fracture. Which is same as, this is same as faceted fracture, which is also same as slip band fracture, slip band decohesion, all that's, all those different terminology. So near alpha, okay, or more volume % of alpha means more crystallographic texture, okay, more crystallographic texture, more planar slip, okay, and more, okay, so let me also make another one up here, more crystallographic texture. This is all the observations over the last so many years. If you put together all these observations, this will be the final conclusion. More crystallographic implies more heterogeneous slip, which is same as more planar slip. Okay? So I just put page 1 Tuesday, that's all. As opposed to or in contrast to less crystallographic texture more homogeneous slip or less heterogeneous or more homogeneous. Homogeneous slip or more homogeneous slip. Less planar slip. Same as more cross slip, and the fracture would be less slip band decoherence, less crystallographic fracture. So this is like a, yeah, I'm glad I wrote that thing down. I think that's important at the end of the, now that we're coming to a closure, I think these are some of the important points that you want to take with you home. So they all go together. Huh? Oh, sorry. So what we're saying is in the near alpha titanium alloys, which have got more volume fraction of alpha, you will have, it goes along with more crystallographic texture, more planar slip, and more crystallographic cracking, okay? All that stuff. Okay. Let me get out of this for a second. Right. Okay. So, okay, let's go here. Okay, I think this is the right slide here. Okay, so we know that the alpha is hexagonal closed packed structure, right? Alpha titanium is hexagonal closed packed structure. So it's got this basal plane. Okay? And then it's got this, yeah, the basal plane is 0, 0, 0, 1, 3 zeros and 1. That's your basal plane, the hexagon, okay? And then A1, A2, A3, and this is like an example of a direction, 1, 1, 2, 0. And this direction is also 0, 0, 0, 1 direction, okay? Which is fine. Yeah, that's okay. That's also the plane. And this is the direction, 1 bar 1, 0, 0. And this is the direction, 1, 1 bar 2, 0. So the plastic anisotropy, essentially in alpha beta or alpha aluminum, alpha titanium alloys, comes because of this phase. Okay? Because if it's only FCC phase or BCC phase, it's very simple. FCC phase, we only have one slip plane 1, 1, 1, the dominant slip plane. We have other slip planes too, but 1, 1 bar or 1 bar 1, 1, 1, 1 type of family of slip planes, are for FCC. And for BCC, I keep biting my tongue. For BCC, it's 1, 1, 0. Okay, that's that. So the plastic anisotropy in near alpha titanium alloys comes because of this HCP crystal structure. More alpha volume fraction, more of this HCP volume fraction will be playing a role in the overall deformation, right? And the titanium alpha phase has 3 known slip planes, basal, prismatic, and pyramidal slip, which I'm going to show in the next picture. Okay, so there is your basal plane. Like I said, it's 3 zeros 1. That's a basal plane. Okay, and there is your 1, 1. Okay, there's your prism plane. This one is your prism plane. Okay, 1, 0, bar 1, 0. If you want to know how to index the prism planes, I do have a set of notes in my thing. We can print it out later. Okay, so let's make a note of it. how to designate these planes may be useful for some people. So I'm not going to use this. I'm just going to put this as a note, give out the indexing of, or maybe we can go over it maybe in the afternoon or something, give out the indexing of the planes in HCP. This is simple, not too hard. HCP crystal structure, okay? Okay. Okay, so here we are. Right, so there is your 1, basal plane with the slip direction, 1, bar to 0. That's the direction. Because every slip system has to have a plane and a direction. And the other one is the prism plane, 1, 0, bar 1, 0, and this slip direction. So these two guys have the same common slip direction, okay? And the pyramidal plane is take any one of these directions in the basal plane, okay, and join it to these opposite corners. That's your pyramidal plane, okay? So there is your 1, bar 2, 2. And there is your 1, 0, bar 1, 1 pyramidal plane. And this one, these two joining to those two is your other pyramidal 1, bar 2, 2. And you can have, again, joining from here to there. And then, yeah, okay? And there is your direction 1, bar 2, 0, which is in the slip plane. The slip direction has to be in the slip plane, right? So there is your pyramidal slip plane. There is your another pyramidal slip plane with a common direction, 1, bar 2, 0. So they both have to be, slip plane and the slip direction have to be involved. Okay? Yeah, I just wrote that same thing there. Okay. So these are important for the understanding the deformation of hexagonal close-packed systems, whether it's zirconium or magnesium, titanium. They're all HCP structures, right? And the hard orientation is the pyramidal slip. I'll show you a figure of the crystallographic result shear stress. That's his favorite stuff. I'm going to have got a graph on that. Hard orientation, the pyramidal slip, C plus A, it's called as. Okay? Slip must occur for plastic deformation. And these are the soft orientations. The basal and the prism slip planes are the soft orientations. This easy slip activation. Okay, so that's good. Now, I said the other day, the creep occurs at room temperature in titanium. It does occur in room temperature, but the only thing is, you only see the primary creep, not the secondary and the tertiary. Only primary, small portion of the primary takes place at room temperature. Okay, even for stresses below, okay, obviously, significant strain can accumulate during creep as a function of time at room temperature. Okay, so Neeraj, Glenn Dane, and Mike Mills, these are the three guys from University of Ohio State University. And I believe it's this guy's PhD thesis, because these guys are professors, Glenn and Mike, I know them pretty well. So, unusual, okay, so this is the data. First, let's look at the data. Stress is about 80% of the yield stress. Okay, it's below the yield stress, 80%. I'm sorry, there. Okay. So there is your 80% of the yield. I feel funny standing here. I can't see the view graph. Okay. Titanium 6211, colony. Okay. 6211 basket weave. So these are alpha beta processed, these two alloys, right? I mean, this alloy and that alloy, colony and the basket weave, and then titanium 5, 2.5. Okay. Look at these strains. So this is what? 1, 2, 3. Okay, 4.2. 4.2%. No, 0.04%. That's the creep strain you're getting in the most bottom one, which is the titanium 5, which is the titanium 6-4. So it's not a whole lot, but it is there, 0.04% creep strain. And if you have the good extensometer, capacitance gauge, that's what they use most of the time to get those kind of strains. And they can put the capacitance gauge outside the furnace. You don't have to put it inside the furnace. You can put it outside the furnace, and it's very accurate, very, very sensitive. Okay? And after 1,000 hours, it just goes over to just about 0.21, 0.22, 0.21, 0.2, 0.3, 0.3, 0.3, no, what am I talking about? Sorry, 0.003, 0.003 creep strain. 0.2 is the slope. That 0.2 is the slope. Okay, I was mistaken for that. So it goes from there to there, the creep strain. And the other data that you see there, they're all like below 0.02. Yeah. So the maximum you get is 0.02, and the minimum you get is that 0.304. So you see some creep strain, and this is by several different authors, okay? Several different authors. And the slope, actually, if you take this equation, that is Andrade's ANDRADE creep. How many know Andrade's creep? Primary, secondary, tertiary creep? Yeah. So this is the primary creep, and this is the law of Andrade's law, right? Where is it? Okay, so in there, Andrade's law. Oop.
So this kind of creep strain up to what temperature?
Room temperature. Whole thing is at room temperature. Okay, Andrade creep. Okay, I hit calibrate like aerial narrow. Okay. Okay. So there is your Andrade creep. And in that formulation of Andrade creep, alpha happens to be 0.2 here. Okay? These are room temperature creep studies. And then in the case of this guy, Neeraj and those guys, I think the slope was a little bit different. It's a little bit different, actually. Unusual creep behavior in the titanium alloys. This is based on strain rate sensitivity. And strain rate sensitivity is defined as, okay, so strain rate sensitivity is defined as, let's say they use the word, they use the symbol M in the literature. It is log sigma epsilon dot, a constant strain and temperature. Okay, that is your strain rate sensitivity parameter. Because this parameter, all it does is it just shows to you that if you change the strain rate, how much does the stress change? So if you're doing a tensile test at room temperature, for example, you come up here, the material is yielded. Let us say you're doing it at 10 to the minus 3, the test. Okay? 10 to the minus 3 per second. And you change the strain rate. Let us say 10 to the minus 2. You go up one order of magnitude, 10 to the minus 2. And then let it go for a while. And then you bring it back to 10 to the minus 3. That's the test. That's the strain rate sensitivity test. From this, you can calculate how much the delta sigma goes up for every delta epsilon dot. Okay? And you can do this for several different rates, actually. And you can calculate your enthalpy for deformation. And also, you can calculate your enthalpy. Enthalpy is not H. Is it H? Is there a symbol for it? Yeah. And then delta, not G. Well, let's put G for now. Activation. So this is your activation enthalpy. And this is your activation energy. By doing the above tests. So you can do these tests at different temperatures, different strain rates, and you can get this whole, you can write a thesis on it, actually. Okay. And they did this kind of thesis back in the late 70s. You do this on every material, one PhD thesis has been produced. So when the materials are, so the alpha titanium materials, according to this work, I'm sure that's what, if you look at the thesis on strain rate sensitivity, that's what you will find, that the titanium alloys, near alpha titanium alloys are very strain rate sensitive. Okay? Now, there is also planar deformation, like we talked about, planar slip. Okay? I don't know about this short range order of titanium and aluminum atoms. I don't know why they're calling it as short range order, but that's what the literature says.
It's ordering in localized region.
Huh?
Ordering in localized region.
Right. Yeah. But actually, it should be on the long range, actually. But, okay. Yeah. Ordering, I think, but the ordering should exist long range. Okay. But that's okay. There's no problem with that. And planar deformation leads to very low work of hardening. So actually, on that page, we can also add planar slip means low work hardening. Cross slip means more work hardening. So I remember my advisor used to get excited when we saw that one time. So there is I'm going to just put an elastic plastic line, planar slip. Okay. Pretty small slope, work hardening slope. And there is my cross slip material. So, yeah, less work hardening. More work hardening. Yeah? Okay. So,
strain rate.
huh?
To measure the strain rate, we are using the capacity transducer.
Huh?
Capacitance transducer.
Capacitance gauge, yeah, to measure yeah.
But the rate of measurement of any quantity can be measured by only LVDT.
Can be measured only by?
LVDT.
Oh, you can measure by capacitance gauge also. It just works on a different principle. Yeah. So in the case of capacitance gauge, is based on capacitance. Okay? Charge is stored in the capacitor. What is
but the rate, whenever we deal with the rate.
No, but you're measuring the strain first and as a function of time, and then you're getting the rate. The capacitance gauge is only measuring the strain. Not the rate. No. Or only the change in the gauge length. You divide that by original gauge length, you'll get the strain, and then you divide by the time, you get the slope. Strain rate.
The inductance cases are used only in case of any rate, maybe velocity, that type of a rate. Whenever rate is involved, inductance cases.
Oh, you're thinking electrical engineering. Yeah.
That is why.
Yeah, you're not measuring, you're right. You're not measuring this rate directly. You're measuring the strain and then dividing it by time, right? Only thing, what I was saying was the capacitance gauge is very, very sensitive to measure these kind of small strains. And you can also put it outside the furnace. Well, so you can, LVDT also, you can put it outside the furnace. But remember the location of the capacitance gauge. If this is your creep frame and your sample is there, the things that hold the specimen and all that, the bar that is there, that's where you put the gauge outside the furnace. That's what I remember, my mental picture. So I'm going to show you that, well, I'm going to show you means I'm going to show Neeraj's results actually, you know, that the interaction between the slip systems is also minimized, okay? So the slip bands are able to pass. Let me show you then, it'll be much easier to explain. Beautiful pictures. Titanium, alpha titanium gives you beautiful TEM pictures. There are two alloys that give you, if you want to be good TEM pictures, work on two alloys. Either aluminum lithium alloys or near alpha titanium alloys. You are going to get such beautiful pictures, mind-blowing pictures. Look at that planar slip. You cannot believe it, how beautiful it is, right? Look at those dislocations. I like it actually, personally. I love these kind of pictures. So there is a slip band. You know, of course, this is a G vector. You have to orientate, this orientation, how you orient it properly. And this is low angle boundary. So that means the boundary here is very low compared to the next one. There is another set of dislocations, another set of dislocation band. Huh? Beautiful. Planar slip 1, 0, 1, 0. So you need this G vector to determine which slip plane it is, okay? Say, yeah. Okay. Planar slip in prism planes observed in a creep deformed 716 MPa, 0.9% strain in a titanium 6 aluminum sample. So it's all alpha. Everything is alpha phase only. And beautiful slip bands. Huh? Another, so that's prism plane. This is basal plane. Beautiful slip bands. Huh? Very nice. Low angle grain boundary. Look at the resolution. 500 nanometers or 50? 500 nanometers. Very nice. Huh? But it's easy to get these pictures. I don't want to make it look like real easy. There's a lot of, you have to sit on the microscope for quite some time. And Ohio State has got one of the best microscopes in the world, actually, I would say. It's specialized in that. The next picture is even more beautiful. Okay, so there is your planar slip, but look at this planar slip bands. There is a planar slip band coming this way, okay? And there is a planar slip band going that way. If you really look at it, there is really no obstruction for this guy because of this. You see the slip band continues. So even though this guy is there, there's not that big of an obstruction. It just plows through it, literally. And again, same thing. With this slip band, there is no obstruction much. They just go through. Because there is no much work hardening. Very little work hardening. If there was work hardening, first of all, you won't have these nice slip bands if it was cross slip, but you'll have a lot of dislocation forests and all that here. A lot of entanglements and all this stuff. So this fits the theory really well, actually, you know. Okay, we have done all this stuff, so I'm not going to go there. Okay, so, yeah, you know, we did all this stuff, if you remember, right? Yeah. Oh. Actually, we did. I wanted to show you this one. So this is one of the, this is where Jim Williams became big, actually. One of the classic works in literature by Jim Williams and Neil Payton and those guys at Rockwell Science Center. This was the measurements performed by Jim Williams, and he was the first author. Critical resolved shear stress, right, on the y-axis, as a function of temperature. As a function of temperature. So essentially at room temperature, 23 degrees C, you can see that this basal and prismatic slip, in order for that to take place, it only requires about that much stress. That much stress. But when you go up here, pyramidal slip, look at how much stress you need to activate that slip, much, much higher. Okay, that's why this is the hard orientation. If you remember this slide we mentioned, Where did we mention? Hard orientations. Hard orientations. Oh, you cannot see my mouse there. So the pyramidal slip is being referred to as a hard orientation as compared to the basal and this is soft orientations. Okay. We did all this stuff. The forging, oh yeah, they're here. So the forging guys, yep. Primary alpha, transformed beta. Okay, this is the duplex microstructure, if everybody remember. Thermomechanical processing to obtain, about the beta trances, like we talked yesterday, or day before, or some other day. This is beta, below the beta trances. When you do the hard deformation work here, you're doing the below the beta region. So homogenization of the ingot, thermomechanical work either here, I keep using it more. So homogenization, thermomechanical work here, which is in the alpha beta region, or in the beta region, right? And you can take it for recrystallization over there, and then annealing it, okay? And then cooling will produce this microstructure there. And depending on the cooling rate, of course, the thickness of this lamellae, alpha lamellae, will be defined by the cooling rate. So this all fits, everything fits very fantastically, right? And we also said this kind of a microstructure is good for crack growth resistance compared to equiaxed alpha. Okay. And then we just talked about that. Okay, now let me just do one thing again. I'm sorry. You have to, let me see the slide sorter. Okay. Let me put up this one. Actually, this one also. We got to do one at a time so that, okay. Okay. So here come the dislocation theories a lot. So a lot of dislocation theory goes in here, but I'm just giving you the just final. So you now remember the prism planes and the pyramid plane. So we got this soft grain. So here is a soft grain, and here is a hard grain. Okay. So slip resulting. So if you have a pile up here, okay, and if you want to transfer it to the next orientation or next grain, for instance, and if this grain is oriented, the next grain that's oriented here is a hard grain, okay? That means it's hard to slip in there. And this slip can take place, but if it doesn't, if you do not have enough stress if the stress for the decoherence of this boundary is less than the stress it takes to transfer the slip to this, then the fracture would take place. Otherwise, the slip would take place. So when we do the crystal plasticity models, those are the kind of things we answer usually from the modeling. Will the slip takes place, or will the decohesion will take place? What is the statistical numbers and all those stuff? If we have time, I may just kind of touch upon it a little bit. Okay. So slip resulting from dislocation pileup in the soft grain is transferred to the adjacent hard grain. The transfer slip in the hard grain results in a planar slip band, which ultimately decoheres as a fracture facet parallel to the basal plane. Well, actually, come to think of it, what I said is a little bit different from what I see here. So either you can have a decoherence here, the other decoherence you can also have is a decoherence here. See this resolution here. I mean the resolved shear stress. You have a sigma which is perpendicular to this. Okay, this can decohere right here on this basal slip plane, 0001. So that's why these days what we do to understand crystal plasticity a lot more, we take these fracture surfaces to the scanning electron microscope and we look at the orientations of these fractured grains so we can relate these fractured grains to this deformation that is taking place, okay? And here is a more detailed paper by, I have this paper in here actually. I'm going to, maybe I'll take this out later on if we, this is from the Royal Society, Federal Royal Society, Royal Society proceedings. This is 2015, so it's quite new actually, quite new, and Dunn is the group leader actually. And there is a bimodal type of a microstructure in a 6-242 alloy, okay? Primary alpha and transform beta, and the hot working was done as a forging in alpha beta field, okay? And that's the microstructure that results. And here are 3 photographs. I think I lifted this, okay. There is your regular fatigue, okay, constant amplitude fatigue. There is your dwell fatigue, and there is your static load. Try to see if you can see any differences between the, no? God, I get thirsty every day. Oops, sorry. Let me see if I wanted to do this. So there is your normal fatigue. What do you see there? Okay? That's your normal fatigue. Even in normal fatigue, let me come over here. In the small, when it was small, you couldn't see this. Even in normal fatigue, you see these regions? Huh? Completely different, right? These are those alpha regions. Even in normal fatigue, you're seeing this. Okay, let me turn that down, go back. Okay, let's go here. There is your dwell fatigue. You have to put this side by side, I think, little to get a little better picture of it, but you can clearly see the difference. I can see that because I'm more used to it. But you can see this, the planar slip band cracking. See this whole thing? That's a planar slip band cracking. This whole thing is a planar slip band. Well, these are little pieces here. There is another, you know. This almost looks like a cleavage in a way, or transgranular fracture, but this is what, that's why, you know, it's like going to the doctor and saying, well, I'm not good, feeling good. He has to check everything. But if you say, well, I have a headache or I have a toothache, then you can focus there, right? So the same way when you're going here, you have to know what material you're working with, what are the tests that you have done, and what is that you're looking for. But if you took a fracture piece to the SEM without knowing what you're doing, you can be there trying to find a needle in a haystack, basically. So it's always important to know your parameters, what is that the test was done under, right? So there is your, instead of doing that, let me just go back. Okay, so let's take the static load, just dead load. Huh? The dead load looks like dwell fatigue load. So this is like a dead load. So it's not fatigue, right? It's not dwell fatigue, it's just dead load. That means Kmax. So this is what it is. Let me put this up. So number one we saw was, let us use the same waveform, triangular waveform. Number two we saw, oops. Okay. On number three we saw, I'm going to put this for a second. This is the dead load, but this gone. This is gone. That's my dead load. Okay? So this is my P max, my P min. P max, oh, P max, P min, or if you want to have a mean stress, there is a mean stress. Okay? So you can have this as your P max dead load. You can keep it here or you can keep it there. Your dead load test. If you keep it here, you get better results because the load is higher. Right? Better results means easier to see what's going on. So if you really want to do a test here, and then you can do a test there and see the differences also. So you can see here the fracture surface was different, right? Here you had this and this combined. This and this combined was this, right? The fatigue form and this dead load was this. This is the fatigue, dead load, fatigue, dead load, fatigue, dead load. So the dead load was 60 seconds, fatigue. I don't know how much it was, 60 seconds. Here, continuously. So that's what you're getting. Huh?
Striations are not found in the case.
Huh?
In the case of constant amplitude loading.
Yeah.
There is no striation is found
Constant amplitude loading.
in the picture.
Yeah.
Striation, beach marks.
Beach marks. You won't see beach marks at this level, at the scanning electron microscope. Beach marks are usually much lower magnification, maybe 50x. So you won't see beach marks here. You'll see more striations. Good point. You won't see striations that much when you're having planar slip. For some reason, we don't see it. Even though the crack is propagating by fatigue mode, when you have a lot of planar slip, you're only seeing those slip, you won't see the striations that much. But if you have a lot of cross slip, then you see much more striations that are much easily visible. I mean, you'll see it, but you have to, play with it a little bit more. But not a whole lot. Always have a hard time looking at slip striations, Now I don't go to the SEM, but when I used to, I used to see more striations.
This mean stress, when it varies, effect of mean stress, fatigue strength.
So you can see right there. So that is your mean stress, right? So this is your mean stress. If you bring the mean stress down here, it will be different from you taking the mean stress up here. So you can take this to more positive loads, or you can take it to more negative loads. You can shift the whole thing down, right, along with this. So you can have less positive load or more positive load. That will affect the...
In terms of the resistance, fatigue resistance, as
Yeah.
the mean stress increases,
As the mean becomes more and more positive, or increases in that sense, it will be more static, more a dead load test.
fatigue strength decreases. Fatigue strength decreases. As a mean stress decreases.
Yeah. The fatigue part will, yes. Yeah. In this case, yes. Yeah. Yeah. Physically, yes, that's what is happening. Okay, let me just put this up again here. So this is from that paper, from the Royal Society paper, which is actually so they call it the rogue grain combination. There is a loading direction, soft grain, hard grain, soft grain again. So it's all about transfer of slip and fracture where it's taking place in those grains, essentially. Okay? But my thinking is that anytime you have a hard time transferring slip, you're going to get a fracture. Yeah. And the rogue grains here, the rogue grains here, how the rogue grains are, oriented also will decide the fracture modes. And there is more analysis of this, which I can show actually.
Is there any method to calculate the stress at the grain transition zone? That is because softer to harder grains goes. So the transitions on how to calculate the stress at that particular time.
How to calculate the stress at that point?
Is there any formula?
I mean, there are no simple formulas. I mean,
The stress required to cross the slip band, cross the boundary.
yeah. Well, you saw here, for instance, Williams. These are experimental results, and also this. See the dotted. One of the two lines is a prediction. There's a dotted line and there's a solid line. The data points are definitely experiments, and usually we show the model results, with a dotted line usually. So the solid line is experimental, and this dotted line is a model, which perfectly matches the experiments. And this is a little bit more involved actually. Yeah, I think it's not. Okay, hold your thought just for a second. Let me do one thing. Okay. Hold your thought. Don't forget it. I'll see if I can pull it up. So here is a titanium 6-4 sample. It's a low magnification. I mean, just showing the SEM, showing the faceted fracture in the dual fatigue. That's what we were talking about. It looks like very much like, all these facets, they all look like plain, like intergranular, or not intergranular, but transgranular cleavage type of fractures. But actually, they're slip band fractures. But you have to know that you're working with a planar slip band material. If you don't know that, then you cannot tell what these are. You can say that, well, I see some features which look like slip bands. They could be, well, they definitely are not cleavage, but they look like cleavage, but they're not. They're no river lines. Yeah. So you have to know the whole thing. Yeah. Okay. Let's go through this, and I'll talk about that a little bit more. After a break, we'll go through this first. Alloy composition, we already said that those containing a high volume fraction of the HCP phase, they're susceptible to dual fatigue, okay, and low volume fractions of beta BCC phase. And the most susceptible alloys contain clusters of alpha grains that have small misorientations with them, the micro-textured regions. I wish I had a picture of that. Maybe I have. Let me see. Okay. See, the thing is this, that in some cases, when you're doing tests like this, you got to keep this in mind. Sometimes when you're doing a test like this with a dwell time, you're not necessarily doing dwell fatigue. You're probably doing creep fatigue test. You may be doing it because at this time you're doing creep, and this is fatigue. Okay? You could be doing that. So, or you could be doing a creep, oxidation, fatigue test. You may not be necessarily be doing dwell fatigue tests. So you have to be, again, these are little complications in the whole business. So if this is a nickel-based superalloy, and you're doing this test at a high temperature where there's a possibility for oxidation, there's a possibility for a creep also, but not necessarily dwell fatigue in this sense, dwell fatigue, then you may be doing a creep fatigue test or a creep fatigue oxidation test. And yes, go ahead. For welding.
We pass in argons to prevent surface oxidation.
Yeah.
So when we subject it to fatigue, can we prevent oxidation? Because we had passed argon.
So you're talking welding.
Yes.
So during welding, you're pushing argon so that you push the oxygen out,
Yes.
so you get a better weld. Yeah, okay. You take that specimen that is welded,
Yes.
and now you're doing a test
On fitting.
at high temperatures, very high temperatures. Yeah.
Can we prevent oxidation because already we had passed on argon?
No, 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 no. You can only do that if you're doing in a vacuum chamber. Because what did you do after all? All you did was you took a nickel-based superalloy and you welded it. It's still a superalloy. Only thing is the structure is cast structured a little bit. The welded structure is cast. It's not a rock material anymore. And if you're now doing a fatigue test, if you're doing a fatigue test, you're exposing that to a high temperature, so oxidation will take place, and so will creep. Yeah. Do you see what I'm saying? Okay. We can also talk about it a little bit more. Okay. Yeah, let's talk about that during the break. So here we're talking about dwell fatigue. So my recommendation to you is this. When you're reading literature, please don't think that the author is completely right. Don't. Question the author and make sure that he or she is saying the right thing. Because sometimes we say things which may not be right. Not intentionally, but we don't know something. We're missing the data points, So don't think that you're doing dwell fatigue. You may not be doing dwell fatigue. This is, specifically alpha beta titanium at low temperatures where we know for sure there will be dwell fatigue going on, dwell fatigue happening. So, okay. Okay, so look at the number 4. A remarkable feature about titanium alloys is the creep at room temperature, right? A phenomenon known since 1949 but not explained. Actually, it was noticed by a guy, I don't remember his name, Atenstat or somebody. I tried to look for that paper a long time ago, I could never find it. It's published in Metals Progress. Metals Progress, 1947, I thought it's 49. But I couldn't find that paper. Maybe we can find it here. That's the first time anybody noticed dwell fatigue in titanium. Okay. Atenstat, Metal Progress. So some have suggested in the literature that creep is a key aspect of cold dwell fatigue because it leads to less stress redistribution and concentration, which is necessary for crack nucleation. Say a mouthful of, a lot of words there. Okay? A lot of words there. I don't know about this. We had to think about this actually more. These are all called as guesswork, right? Maybe guesswork is not the, what do you call those kind of statements where you make statements without proof? Hypothesis or something, yeah. You don't know for sure, so that's why you do experiments and theory, to prove those things, right? You think that something is true, and then you do the experiment and theory, and then you say, well, that's not true, what I thought. Okay, and then fracture morphology, Okay. How about we take a break here? Should we take a little 5-minute break? Is it okay? Just a 5-minute break. I'm finding it hard to speak 2 hours at a stretch right now. In this case, in this one.